Okay, so this next question is from Dylan, and I'm still waiting to see if Dylan will let us use this image. I hope it is. You won't be seeing this if we can't use this image, but if you are seeing this, Dylan was kind enough to let us use this, so thank you, Dylan, for letting us use your CAD image in this example here. This is a pretty advanced question, too. So if you are not an advanced user of GD&T, if you're not a design engineer, or maybe an inspector, you probably don't need this question, but this is a very helpful question for those of you understanding kind of datum reference frames and how we can use the position tolerance to really control any feature in any orientation or location. So the question was, they have a question about dimensioning the holes on different planes. So if you look here, these holes right here, these 4 holes, are all going to be dimensioned, but his requirement is that they are all normal to this profiled surface right here, this odd-shaped surface. It's not a plane, it's a curve. And the position of the holes are relative to each other is important, as well as their location on the profiled surface on the bottom. So they need to be oriented to that curved surface, but also correctly oriented and located to each other. So in this case, we have a few different ways that we can go about this. So there's kind of an easy way and kind of a complicated way. Both will depend on how tightly required is it that these holes truly are normal to any given line element on this profiled surface. And it also would depend on how perfectly curved this profile surface is. So if we had a profile tolerance on this of, let's say, maybe a 1,000th or less, then you may want to use it, as we'll show you, as a datum, and dimension everything to it. However, if this is a very loose profiled surface, and there can be some small error between the orientation of the hole and normal to it, I would say maybe greater than 1,000th or so, we can do it the simple way. So let's first start the very simple way. The simplest way to dimension this would be to really make the bottom, or I guess this is called the top plane here, your datum A. And then you could make, it really doesn't matter where your other datums are. You could do datums B and C here, or you could just dimension the holes just to datum A in this case. So what we would do is we would have datum A there, and we'd have position. Let's say that you wanted to position these within 1,000th. Again, it all depends on your functional requirements, what is required. But we have this position to datum A. Let's say like this. Now, if we had datums B and C, if they had to be positioned from the walls in a tight way, I'd probably do that in this specific case, maybe to, this surface and that surface. Let's say that we had B and C on here as well. B being the plane on the side here, and then maybe C being this plane, or maybe you have another feature that's more important to dimension to. But let's just assume that, just for simplicity's sake, that we're doing this with A as the primary datum, A being this flat top surface, something that we can pull a direct plane from. Well, in this case, you don't actually need B and C here, because you could just have a 4x position of these holes. Let's say that they're 10 millimeters or 10 inches or whatever, plus or minus 0.005. Let's say that they're 5 thousandths in size, plus or minus 5 thou in size, and that they're 10 inches large. I know that's these don't look like 10 inches, but doesn't matter. The numbers don't really matter in this case. So what we'd have here is, positioning the holes to A, B, and C. Now, the difference is, though, is that we do not want these holes to be normal to that back surface, right? We want them to be normal to this surface. So if we are going to do it this way, it's now up to the designer to actually figure out, well, what is this angle here for these holes? What is that angle going to be that makes it normal to that surface? And again, maybe it's perpendicular, or maybe it's parallel to datum B, but it's at some sort of angle. Maybe this is 75 degrees or something like that. Well, what you would do here in this one method would be you'd put a basic angle of 75 degrees on those holes right there. And then you'd also dimension maybe, this one right here, 75 degrees, all of that. And all we're doing with this is we're saying in a perfect world, if this is a perfectly flat plane, this is exactly where these holes would be. They'd be at a 75-degree angle to datum A. They'd be maybe parallel to datum B. Maybe you set, if there was some angle that to datum B, now you have to make that in there as well. You'd have to have basic dimensions. Let's say it's like 45 between where the hole axes start. But all you're doing is you're really laying out, if I was going to plan where the axes of these holes were in CAD, where would they be in a perfect world related to datum A? And that's all you have to do. You just set them up in their perfect state using basic angles and basic dimensions to get where these true positions are. And then this cylinder is just the true position around that perfect location at that angle. So what you're doing is you're saying all 4 of these holes have the same true position, but they're all at different angles, and that's perfectly fine. They could all be, as long as we give enough information of where each hole is in 3D space. It's X, Y, Z, and UVW, relating to whatever datum reference frame we have, A, B, C. We now can perfectly locate them, and then we'd probably add some sort of profile tolerance to that surface using basic dimensions. So maybe there's some sort of axis way out in space, and this is a true curve. A perfect cylinder, it's a part of a cylinder. So this has just a radius on it. We give that a basic dimension. We list how far the axis of that profiled surface would be from datum A. And we give the profile of, 005, maybe it can be, back to datums A, B, C in this case. And so now what we've done is we've said, all right, in a perfect world, we have just located these 4 holes in 3D space, and we've just located this 3-dimensional surface, this curve in 3D space. We give it some sort of radius. We give it how far that radius is from datum A, so we need to give it a size, location, orientation, and form. But remember, if we give it a size, it has a form, due to rule number 1. And if we give it a location relative to datums, most likely we're also controlling the orientation if we have A, B, C here. So again, that's a simple way, and I know it sounds complicated, but that would be the simplest, or that would be the way that the inspector would probably like this the most. Because then they'd either take the CMM and they'd set this part up on A, B, and C, which are all flat planes, hopefully, or easy to set up planes. And then they would have to enter in, though, where all these true positions should be, so that when they are measuring the holes, they're trying to determine where they should be in 3D space and comparing it to where it actually is. But once again, all we're doing when we're setting up datum reference frames is we're setting up, all right, in a perfect world, this is what it would look like. Or in my CAD world, this is what it would look like. But then this is the error from the perfect world. This is the error that the axis would actually be. It could be angled or it could be out of position, both of those, orientation and location in here. How far it could be from that true location. The thing that makes this complex is not the GD&T. It's the fact that these holes are at a weird, awkward angle. Remember, if you weren't using GD&T, you'd still have to have these dimensions in there. Only now they'd have to use them all separately to try to control this axis somehow. Where here, we're just giving the perfect location in space based on our datums. The CMM can set that up as long as the CMM knows where our datums are and knows where our holes should be, their perfect locations. It can now compare where they are to where they should be and give us how much error we have. The same thing is true for the profile itself. We're saying, hey, in a perfect world, this is where this weird curved surface would be. The CMM now measures it and sees how far away that it is from that true profile, and it just needs to fall within that tolerance. So the GD&T does make it simpler in this case. Now, I did mention that there is a more complicated version of this. When I say more complicated, it's not necessarily more complicated for design. It's just a little bit more complicated for inspection in terms of datum setup. The other thing that you could do is you could make, instead of making this two datums A, B, and C, you could first make the profile tolerance, and this is what I was mentioning. If this was maybe like a really tight profile tolerance here, let's say of 0.001, and again, this would have to be to some sort of reference frame. Let's say the back side of the part, the side of the part, and there. So we make that to A, B, and C. So we first set that up. Then what we do is we say, well, we want the position of these holes positioned relative to this data as a datum. Now, something complicated happens when we use a curve as a datum here. If you are not using datum targets, we mentioned datum targets a lot in our advanced course. So again, this is a very advanced method. So make sure you're in the advanced course to understand a lot of this concept here. But if we were doing this and we weren't using datum targets, the second we make this, let's call this datum D, that curved surface. So we have that profile, and now we make this, which is right there. We now make that datum D. Well, as soon as we do that, if it is not a plane, a datum defaults, if it's like a curve or a cylinder or things like that, if you're using a surface, a datum automatically defaults to the axis of that. So what we're doing when we call out this datum D, what we're calling out is if this was a perfect curve and it made a full cylinder with that curve there, that would have some sort of axis. That axis way out in space, and remember, it depends on how truly big this radius is, that is what datum D is. Now, that's okay, because if you truly need these holes, if you think about it this way, to be normal to this surface, a way to do that would be to make it so that the axis that is created by this curve, which is way out in space, way here, what you'd want to do is make sure that all of these holes all intersect with that axis that may be way out in space. Remember, if this was a small radius, the axis is pretty close to the feature. But the wider this is, the wider that this curve is, the bigger the arc, the bigger the radius, the further out that radius would be. But really what this does is you're making sure that the axis of these holes intersect with the axis of the cylinder formed by the surface. That would make sure that they are also normal. That is the definition of a normal 90 degrees to a curve. It would have to intersect with the axis of that curve, right? That means something is normal. So that's what we could do here as well. And then we could say, all right, well then we are positioning these with a diameter. Let's say it's a tight tolerance again, 0.001. And now what we're using is our primary datum. We're saying, well, the main thing is for it to be positioned normal to that surface. Well, now all we have to do is add datum D here. And then, that will actually control, remember, a cylinder or an axis as a datum controls 4 degrees of freedom. We talk about this in our primary datum lesson in the Fundamentals course. But that datum there would be an axis, and it controls the 4 degrees of freedom. So now the only thing that these holes can do is they can rotate right around that, and they can go up and down. But they can't move in any other direction. They have to stay pointed at that normal surface. And that's kind of what we want, right? So if you just wanted to locate the 4 holes to each other, but you didn't care kind of where they landed on this block, you could just kind of leave it like that. That being said, though, if you did want to make sure that this was controlled here so that the hole couldn't swivel in that direction or that it couldn't go up and down, now is where we can add our B and our C, which will just lock it. So if we had, let's say that this surface, that plane right there is datum B, well, now that's locking the hole so it can't go up and down. So we had datum B there. And then we have datum C, let's say, as just the side of the part. That means that now it can't rotate in any direction there. And remember, if we have 4x on here, the same rules apply to all 4 holes, even though they are in different locations and orientations. That's perfectly fine. We're just saying that wherever these holes are in their true position in 3D space, regardless of which hole we're talking about, this is the tolerance around that hole. Now, to finish this up, we'd have to make sure that we are clear with what we're controlling things to. So you still would have to dimension, because after all, if you had this profile tolerance here, we would need to give it some sort of radius, right? And an axis. Well, where is that datum D axis in 3D space? What is the radius? So let's say it's, 50 inches away. Well, we'd need a 50 basic dimension there to make sure everyone knows where that is. And we'd also need to make sure that everyone understands, is the axis centered to this part? Like in that direction? Or does the axis over there? Is the curve kind of warped? So we'd need to basically make that in basic dimensions, locate how far over is that center line. You can't just assume center. Remember, how far centered is that axis to that datum C that we built there? Datum D doesn't really matter in this case that much, just because, the curve will exist up or down. It's not really controlling anything, but you still may want to include it to A, B, C, just so that when they're doing the part setup, they lock it to datum B as well when they're inspecting this, this profile tolerance. So remember, the hardest part about this is first establishing where this datum actually is and where that is in 3D space. The other thing that makes this complicated is the inspector now needs to first make sure that this, the inspector needs to make sure that first this profile is met. So this is a completely separate requirement than this altogether. So the inspector will first go in and establish datum B. Is this verified? Because after all, if this was not verified, if this profile was maybe not centered, or the radius was incorrect, or it was curved too much, things like that, the form error, location error, size error, all of that stuff. If this was out, well, then these are going to be out because we're relating these based on those datums. So the inspector would have to do this no matter what with both examples that we did. They'd have to check the profile. They'd, touch off on the surface a bunch of times, and they would verify, is that surface within its profile tolerance zone. Be sure to check back with the profile lessons that we have for more information on that. But now here's where the tricky thing comes in for the inspector. The inspector now needs to somehow, in their CMM or virtually in some way, you really can't do this using like gauge blocks and things like that. The previous example, you might be able to use gauge blocks to set up your datums. In this case, you need to set up that, remember we said that it was 50 inches away. You would need to somehow set up this axis. This is not a very good surface to create an axis from an inspection standpoint. And the reason is because if you think about it this way, if this curve ended up being a little wider or a little bit more narrow, this axis could drastically change in location. So let's say the target was it to be 50, but if this went out even just a couple fractions of an inch and made it wider, made the curve larger, well, now this axis would shoot way out because now our circle is way larger that the axis is the center of. So that's why it's very difficult to do something like this in the inspection side. You would need something like a laser scanner or a CMM to do this. So if you did have a laser scanner or CMM though, what you would do is when you're inspecting this control right here, you would then tell the CMM that this is the wall of a cylinder and to give you some sort of axis. So it would find the axis out in 3D space. It would then use that axis to do what we talked about before, which is then when you go to inspect those holes would have to be perpendicular or normal to the surface and really intersect in that axis. So we'd still do the same thing. We'd have our position tolerance, which is right there, But now the CMM would have to build this kind of virtually itself. So first the CMM would have to build that axis out in space based on where you told it was based on that surface, right? Then it would have to say, okay, well, these holes, and this is very difficult to do in programming, are normal to are intersecting to this. You could build a virtual axis essentially to all of these holes, to that axis, to those holes there. And then you have to say these holes are to be in position to that axis. That axis there that I just created is the perfect example, but this is the error that we can have. Then when you go touch off on the surface on your holes and you see the imperfect hole, you're now comparing it to the true position, and you have within 1,000th of that axis to be within tolerance. So although this simplifies things on a design end, and honestly, this is the right way, well, actually, there's no right way. I shouldn't say that. But this is the simplest way from a design standpoint and from an understanding standpoint how to do this. If you do have a CMM and you do have a laser scanner or things like that, it may be very easy to program this. So it is simple. But just understand that if you're sending this to a machine shop, if you're sending this to a place that may not have the way to set up virtual axes like this, you may want to reconsider a different inspection method or allow them to use datums A, B, and C and give them some sort of reference basic angle to do their inspection from. Remember, inspections, you can have an inspection plan that is separate from the drawing. The rule of thumb for your drawing, though, is that in 100% of the parts need to meet that drawing at the end of the day. You can, though, come up with some sort of inspection plan as long as your customer or as long as the design engineer agrees on it, if it does simplify the inspection of this. So what we're doing here, though, what we've done in this complicated method, I guess you could call it, is simplify our drawing, but we now need to make sure that in our inspection plan that everyone knows what they're actually doing and that they actually can inspect it this way. So hope this helps. I know this was a little bit of a long one, but this is a really good example to go through. Very advanced. So from a design standpoint and from an inspection standpoint, I hope this helps a bit. Let's move on to the next one.